Okay, so forms of quadratic functions. A quadratic function is a polynomial function of degree 2. The graph of the quadratic function is a parabola. The general form of a quadratic function is f of x, which is equal to ax squared plus bx plus c, where a, b, and c are real numbers, and a does not equal 0. And the standard form of a quadratic function is f of x, which is equal to a times the quantity x minus h squared plus k, where a does not equal 0. And the vertex hk is located at the following. We can see that h, which is equal to negative b over 2a, and k is equal to f of h, making h the input of the function, which is also equal to f of negative b over 2a. Now, if we're given a graph of a quadratic function, we want to be able to know how to write the equation of the function in general form. The first step is to identify the horizontal shift of the parabola. This value is h. We identify the vertical shift of the parabola, and this value is k. We're going to substitute the values of the horizontal and the vertical shift for h and k in the function f of x, which is equal to a times x minus h squared plus k. And then we're going to substitute the values of any point other than the vertex on the graph of the parabola for x and f of x. And then we're going to solve for the stretch factor, the absolute value of a. And if the parabola opens up, then we know that a is greater than 0. If the parabola opens down, then we know that a is less than 0, since this means the graph was reflected about the x-axis. And then we would expand and then simplify to write in general form. For example number 2, we want to be able to write the equation of a quadratic function from the graph. So we want to be able to write an equation for the quadratic function, which is called g in figure 7, as the transformation of f of x, which is equal to x squared. And then we're going to expand the formula and simplify terms to write the equation in general form. Now, because this is a parabola, this is the reason why it starts with a base of the form of f of x, which is equal to x squared. Now, if we take a look at the graph, we can see that f of x is equal to x squared. And what's happening is that if this is where the original graph would be at the origin, what we've done is that we shifted it to the left 2 units, and then we've gone down 3 units, given a formula in the form of g of x, which is equal to a times x minus, well, it's shifted over negative 2, parentheses, squared, minus the value that it shifted down, which is minus 3. And so therefore, we would end up with a times x plus 2 squared minus 3. And now we need to figure out and pick a point on the graph that would make sense for us to use. So the point that makes the easiest point on the curve is the y-intercept. And if you look here at 0, negative 1, we can choose that point where 0 is x and y is negative 1. And then what we can do is we can plug it into that form. So we can say that g of x is equal to negative 1, which is equal to a, and we can say that x is equal to 0 plus 2 squared minus 3. And what this does is this allows us to be able to solve for the value of a. So we get 2 squared, which is 4 times a, and if we add 3 to this side, we get 2. And then we divide by 4, and therefore the value of a is equal to 1/2. And now we can go ahead and plug all this information back into the standard form. So the algebraic model for this graph is g of x, which is equal to 1/2 times x plus 2 squared minus 3. And then to write this in general form, we basically expand the formula and simplify the terms. So what we're going to do is we're going to go ahead and multiply this out, which is x plus 2 squared, which becomes x plus 2 times x plus 2. You can FOIL that, which becomes x squared plus 4x plus 4 times 1/2 minus 3. And now what we're going to do is we're going to take this 1/2 and then distribute it to all of those terms, which gives us 1/2 x squared plus 2x plus 2, and then we're going to subtract 3. And then we're going to combine those terms. So we end up getting 1/2 x squared plus 2x minus 1. And then you would notice that the horizontal and vertical shifts of the basic graph of the quadratic function determine the location of the vertex of the parabola, and the vertex is unaffected by the stretch or compression.